Hello everyone. This is in continuation to part 1 of recurrence relation. This is chapter 9 of C.L.Liu. I hope you have understood the concept of what recurrence relations are, and to identify linear recurrence relations with constant coefficient, and also find the order of the linear recurrence relation. Now next, as we discussed in the previous part of and also written in the notes, we want to find what is the solution of a linear recurrence relation with constant coefficient. And as we had discussed in the previous part, the solution is basically your numeric function. Okay. Now in this equation 1, as you can see, I have just rewritten the linear recurrence relation with constant coefficient. What this equation is: C0 AR plus C1 AR minus 1 plus C2 AR minus 2, and goes on till CK AR minus K is equal to FR. And now to find a solution to the this linear recurrence relation with constant coefficients, and we will extensively be calling the difference equation, you have to find the total solution, which is the sum of the homogeneous solution and the particular solution. Now the homogeneous solution is one which satisfies the difference equation, keeping the right hand side of equation 1 equal to 0. That is C0AR, and then we put a H in the superscript just to signify that it is a homogeneous solution, and you get the equation 2. And all the solutions, homogeneous solutions that you have, they are depicted at A0H, A1H, ARH, and so on. Okay, in the same way you have a particular solution, and for the particular solution the equation looks similar to equation 1, and we get equation number 3, and all the particular solutions are written in the form as A0P, A1P, and so on. Okay, so to find the total solution, we have a sum of the homogeneous as well as your particular solution. Now you would say that in a homogeneous solution, as you see in equation number 2, the right hand side, which is FR, we have to find that solution, homogeneous solution, FR we equated to 0. So why do you actually use, or why do you actually need a homogeneous solution? It is required because the particular solution alone will not be able to satisfy the boundary conditions. Now remember, for a kth ordered linear recurrence relation with constant coefficients, to uniquely get a solution, you need to have k boundary conditions. Okay, now in this particular section, or this particular note, we are basically talking about how to find the homogeneous solution. So the homogeneous solution of a linear recurrence relation with constant equation, or just a linear difference equation with constant coefficients, is of the form A alpha 1 to the power of r, where alpha 1 is your characteristic root, and A is some constant which can be determined by the given boundary conditions. Now if you substitute A alpha to the power of r for AR in the equation 2 we had in the previous page, this is the characteristic equation you get. Now I believe you now would recall what I was saying in the previous video, that you have done this earlier in class 11th or 12th, to find what the different characteristic equation is, or difference equation, and then find the characteristic roots, and that is exactly what we need to do for the homogeneous solution. We write the characteristic equation, and then we find the characteristic roots. So characteristic equation of the kth degree has k characteristic roots. Okay, now the thing is, the roots that you get once you have found the characteristic roots, the roots that you get, are they k distinct roots, or are they some roots which are duplicate? For example, k distinct roots, if I have a difference equation and it is of order 2, so that means I should get, or I will get 2 roots. Now if the 2 roots are 1 and 2, so that means these 2 roots, they are 2 distinct roots. Okay, and the other cases when there are duplicates or triplicates. That means if I have two roots and the two roots are 2 and 2, so that means the root 2 has multiplicity 2. Okay, now so your homogeneous solution will vary. The way you write the equation for the homogeneous solution will vary, whether you have distinct roots or you have roots with multiplicity say m. Okay, so if you have k distinct roots, so if alpha 1, alpha 2 and up till alpha k are the k distinct characteristic roots, and a1, a2 up till ak are constants, then this is the equation. AR homogeneous equation is a sum of a1 alpha 1 to the power of r plus a2 alpha 2 to the power of r up till ak alpha k to the power of r, where all these a1s till ak, ais, all of these are determined by the given boundary conditions. Okay, so it is a sum of some constant into your root to the power of r, and each of these terms is added for each of the given distinct roots that you have calculated. Now, for example, the Fibonacci series that we were considering, the recurrence relation is of this form: AR is equal to AR minus 1 plus AR minus 2, with the two given boundary conditions: A0 is equal to 1 and A1 is equal to 1. Rearranging terms, we get this equation 1, and hence the characteristic roots you have alpha square minus alpha minus 1 equal to 0. So as you can see here, it's a second order difference equation, and you will get two distinct roots. And to find the homogeneous solution, as we saw in the previous example, here I can show you the equation up here. So you have a1 into alpha 1 to the power of r plus a2 into alpha 2 to the power of r. So hence you get equation 3. Now generally in a question, if they asked you find the solution of a linear recurrence relation with constant coefficient, so a solution generally means that you have to find the total solution. So that means you'll have to find the homogeneous solution as well as the particular solution, add the both of them, and then apply the boundary conditions to get to know what the constants are, a1s, all the i's. But in certain cases, if they ask you just to find the homogeneous solution, so in that case, just to find the homogeneous solution, you would try to find the value of your constants AIs, A1 and A2 in this case, by using your boundary condition. And that is what I have done in the next few lines. So you can verify that. Okay. So that's how you use a0 value and a1 value, and you get two equations and two unknowns. You get equation 4 and 5 and two unknowns, a1 and a2, and then you solve to get the value of a1 and a2, and then substitute it in your equation 3, which is your homogeneous solution, and that is the last line. That is the answer you get. This is the homogeneous solution. So you have substituted the values of your a1 and a2 by using the boundary conditions. Okay, now take another example, and this is in fact from the back exercise 9.1a. So you're given a linear recurrence relations and you're given two boundary conditions, and from this you can see that it is a second order linear recurrence relation with constant coefficients, and hence the two boundary conditions, you're given two boundary conditions, two consecutive terms, you know that you'll be able to find a unique solution. So your characteristic equation becomes equation 2, alpha square minus 7 alpha plus 10 equal to 0. Remember, the FR on the right hand side has to be equal to 0 if you have to find the homogeneous equation solution. And your characteristic roots, these are your distinct roots 5 and 2, and your homogeneous solution will become ARH is equal to A1 5 to the power of R, which is your alpha 1 you can say is 5 and alpha 2 is 2, plus your A2 into 2 to the power of r. Now if you want to, I've written this specifically, if we want to find just the homogeneous solution, we will use the given boundary conditions a0 equal to 0 and a1 equal to 3 to solve for a1 and a2, else leave it as equation number 3. So if you have to find the total solution, you will stop here After finding or this equation number 3, you'll just stop here and then you'll go on to find the particular solution. You will apply the boundary conditions in the end. So you have to really remember this, otherwise you will get an incorrect answer. So suppose in this case I just had to find the homogeneous solution. I have applied the two boundary conditions, got two equations in two unknowns, 4 and 5, and I solved to find the value of a1 and a2. Hence my homogeneous solution, which was in equation 3, I get it as 5 to the power of r minus 2 to the power of r. Okay, now the other what we were saying was, the other thing was that your roots of the characteristic equation are multiple roots. So if alpha 1 is a root of multiplicity m, the corresponding homogeneous solution is, so remember when we said the total, the homogeneous solution is a sum of the terms a1 alpha 1 to the power of r. Now that term would be different if your alpha is a multiple root of multiplicity m. Okay, so you have, in that case, that particular term will become a1 r to the power of m minus 1 plus a2 r to the power of m minus 2 up till am minus 1 r plus am into alpha 1 to the power of r. So ai's are determined again by the boundary. So it looks like a very big equation, but generally it's we are not working with very large kth order linear recurrence relation. Usually the questions that we are working with, they are just like two or second order or third order. So at best you'll have a multiplicity of 3, so you won't have a large term here. So consider this, the difference equation given as an example 9.2. So you can find, you see that this is a difference equation which is of order 3, and the characteristic equation becomes alpha cube plus 6 alpha square plus 12 alpha plus 8 equal to 0. And here you have minus 2 is a triple characteristic root. Okay, so m here would be 3. That means the 3 distinct roots that you are getting are minus 2, minus 2, minus 2, and hence you say minus 2 is a triple characteristic root. Okay, so as we see in the above equation, you will just apply the value of m and you will get, and you have just one root, but it is of multiplicity 3, so you will have just one alpha 1, so it's minus 2 to the power of r, and you have a polynomial here, alpha 1 r square plus alpha 2 r plus alpha a1 r square plus a2 r plus a3 into minus 2 to the power of r. Okay, this becomes your homogeneous solution. Seeing another example, you have a difference equation 4ar minus 20r minus 1 plus 17ar minus 2 minus 4ar minus 3 equal to 0. So again, it's r minus 3, so you know it's a third order linear recurrence relation. This is your characteristic root in the next line, and you have you'll get obviously 3 roots. Here the characteristic roots that you get are half, half, and 4. So half has a multiplicity of 2 and 4 has obviously a multiplicity of 1. So that's how you get your homogeneous solution. Okay, so I hope it is clear here. So next you can do is you can try a few questions from the back, and I have written answers to help you actually cross check whether they are correct or not. Okay, just go through the notes as well as this, and I hope you'll be able to understand. Okay, thank you.